Pleasure to be with everybody today. Last time we had glitches because we were still dealing with the aftermath of Hurricane Maria, but both the internet and the electrical power seem to be a lot more stable now, so hopefully we'll go through without any problems. So what I'd like to talk about today is monitoring of reservoirs for sustainable use, which is a little different from and more complex than the monitoring that's normally done just to see what happens in the reservoir over time if you're looking at a life of reservoir type approach. In sustainable sediment management, we're seeking to minimize the rate of volume loss. We're trying to achieve a balance between sediment inflow and discharge. We're trying to maximize storage or other benefits, and we want to do this while minimizing environmental and social impacts. So as our reservoirs age, which we interpret to say fill with sediments, we're faced with a condition where we, as a present generation, did not pay for the construction of most of today's reservoirs. Reservoirs were really, a lot of reservoir construction occurred in the 1950s, 60s, and up through the 70s. And today, these are paid for, and we're benefiting from our parents' investments. So to sustain these benefits, we have to be prepared to invest in the upkeep, which becomes sediment management. So what we're looking to do is identify and implement sustainable strategies that will provide long-lasting benefits at acceptable levels of economic and environmental cost. So if we compare the sustainable versus conventional management, in the conventional sense, reservoirs, you determine the sedimentation rate, you assign a sediment storage pool, and you assign a reservoir life. What happens at the end of the life is not addressed by the original designer, and it's just an open-ended question. But today, as reservoirs start reaching the point at which they're affected by sediment, we can't just throw them away and build new ones. It's not like getting rid of an old car. You can't recycle them, etc. We have to deal with what we've got. There's very limited additional reservoir sites, and this leads us to the sustainable paradigm, minimizing volume loss, balancing inflow and discharge, and we want to maximize long-term storage or other benefits. So whereas in the conventional type of situation, we're basically tracking the decline of reservoir function over time. We're looking at basically changes in the storage elevation curve. We may look at sediment encroachment onto infrastructure, and bathymetric studies alone are generally sufficient for this purpose. And the bathymetric data are typically presented in this form of a storage elevation curve. And while this does illustrate the impact of sedimentation on different pools, it doesn't help conceptualize the sedimentation process. Now, can you see this arrow that I'm moving around here?
We can, yes.
Okay, so you see here we've got on the left a series of storage elevation curves, sedimentation over a period of years, and this tells you what's happening with the storage volumes, but it doesn't give you good information on what type of deposit patterns are occurring. It doesn't show how close a delta may be to the dam or to an intake, and the delta is important because the delta typically contains sandy sediments, very abrasive, whereas the sediments that may be on the bottom of the reservoir are fine-grained sediments, silts, and clays, and typically not very abrasive. So it does not give you a good conceptualization of the process. Sustainable management is much more complex. You're not just looking at how the reservoir is infilling. You have to take mitigating actions both within and often outside of the reservoir also. Outside activities may include, for instance, implementing demand management because you may be faced with reduced water supply, and you may look at water conservation as one of the suite of alternatives that you may implement to help combat the sedimentation problem. You may have conjunctive use of ground and surface water. A lot of work like that is being done now in California. But basically, if we look at the different alternatives that are given to us for management of sediment, we see we have basically 4 different types of activities. We can reduce the sediment inflow, we can route sediments, we can remove deposited sediments, or we can adapt. And to identify the proper strategy or combination of strategies and to design the works or changes in regulating rules, operating rules that are required to implement, and also to determine how effective they are, we need to do monitoring. So monitoring is something that's required for all of these sediment management options. And as you can see, the variety of types of activities here is much broader than simply letting the reservoir fill with sediment and predicting when that's going to happen. So this, in turn, means you're going to have to have more data. So before moving forward, I would like to briefly just give a quick overview of the sedimentation process that typically occurs in a reservoir. You typically have a delta, coarse sediment, that begins to accumulate upstream. Then you have bottom set deposits, which are fine material that extend beyond the level of the delta. Deltas will generally have a relatively uniform top slope, but you may also find deltas perched at different levels. But this transition from the face of the delta to your bottom set deposits typically corresponds to a pretty abrupt change in grain size. You're going to have sand here, and you move a kilometer or so downstream, and there's no more sand. And all the way to the dam, it's fine material. And you also have these horizontal beds, which can occur if you have what they call muddy lake deposits. So here is some deltas. This is Tarbela in Pakistan. This is Silton sand, 50-50. Here we have a reservoir, basically cobbles and gravels up in the Andes. So you can have a large range of variation in the size of material in your deltas. This is a delta showing you a simple sand material. And as the reservoir is drawn down every year, this is for hydropower production, you'll see that the delta material gets eroded away from upstream and transported further downstream and pushes the delta face further downstream. Here's an example of delta movement from a reservoir in Haiti. And you can see that all of the additional sedimentation occurs in this area here between the red dotted line and the new dark line. And this corresponds to a constant operating range over the years. See in the upper part of the operating range, there's very little sediment, additional sediment deposition. It's all moving downstream. So your deltas will tend to advance pretty rapidly towards the intakes. Now, in the delta in particular, you will find different types of sediment. It's not uniform material. And when you're trying to monitor and document what's there, it's important to keep this in mind, because if you take a sample from the very top of the bed, if you've just had a flood, you're going to get a lot of sand. If you wait until next year, there's been no flood, you're just going to have fine sediment, or maybe just some organic material. So taking a surface sample, like an Ekman dredge or something like that, and a little handheld surface sampler, is not going to give you the data that you need. You want to get a core, and the core should go as deep as possible. So the fine sediment is fine materials that is deposited downstream of the delta. And you would have beds which are, if they're seasonally dried out, they will look like this. But it's typically very fine sediment, and it's rather uniform in its distribution. You do not have typically the problems of variability in sediment grain size and composition in the fine material that you definitely see very markedly in the delta. Now, turbidity currents, we mentioned a little bit ago, it's a sediment-laden inflow The sediment imparts a lot of density to the water. It plunges beneath the clear water, runs along the thalweg, and deposits as a muddy lake. And so you see these horizontal deposits. Now you can have density currents which don't transport a lot of material to the dam. And in that case, you would have a bottom which would be sloping all the way to the dam, essentially. But these horizontal deposits occur when the turbidity comes in. It creates a lake of muddy water underneath the clear water, and then it deposits out of that muddy lake. And this is a clear indication of sediment that can be released. If you can release the muddy lake, just, like the flow of water, you can get the sediment out along with it. This is a picture of a small reservoir in Puerto Rico showing turbid water entering the reservoir. It flows beneath the surface, and here it comes out as turbined water because the turbines that are intake is at a low level here. So you see that it does enter, flows beneath, and comes out downstream. And this is the release of fine material out of this reservoir. So if we want to monitor for sustainable use, we are going to look at data we need to predict the impacts on the beneficial uses in pools. This is something we already should be doing with conventionally, but then we need to have data to understand the sedimentation process and the patterns. We need to identify what type of management alternatives may be appropriate, and we also need the data needed to implement them, whether it be a change in operating rule, structural changes, or both. We need data for the calibration of models, and these models are necessary to develop these operating rules. And then we need continuing data collection to continually monitor and improve our sediment management results. And sediment yield is highly variable over time and space, and understanding and managing this variability is the key to many of these sediment management alternatives that we have before us. So basically, to convert an existing reservoir to a sustainable reservoir, document the pattern and rate of sedimentation, perform a sustainability evaluation to identify the strategies and data needs, and then begin implementation. Collect your data, design, implement. And it's also important that different sediment management techniques will be appropriate over time as sedimentation progresses. For instance, in a brand new reservoir, I can release a turbidity current. But over time, that turbidity current may no longer reach the dam because if it originally flowed down the original river channel and that gets filled in with sediment, that turbidity current may stall. Whereas if I lose a lot of capacity, then I can start doing things like flushing or sluicing, which would not be possible when the reservoir had a large storage volume. So these things will change over time. So first of all, let's start with the volumetric surveys or the bathymetric studies. Why do we need these? We need these to update the storage elevation curve. We want to plot successive volumes over time to see the sedimentation rates changing. We want to plot longitudinal profiles and understand how the sediment is advancing along, basically the delta. And we want to monitor encroachment on the critical infrastructure, intakes, navigation channels, marinas, etc. The challenges we have on bathymetric surveys is number one, the consistency, or I should say inconsistency of survey data as a result of evolving technologies. Many reservoirs were designed, if you built a reservoir in the 30s or 40s, your original survey might just consist of data off a topo map. We don't know what level of data originally went into the original photogrammetric survey or other survey that was used for pre-impoundment conditions. And you may come back after 20 years or so and make an initial survey, and you're comparing one methodology, which is a survey for dry conditions pre-impoundment, against a survey which was performed post-impoundment with different levels of accuracy, etc. That's why it's always good on a new reservoir. The first thing you should do when it impounded for the first time, make an initial survey and try and maintain consistency of methodology. The second problem we have is budgeting the repeated surveys we need to detect changing trends. Budgeting of surveys is always seen as a secondary importance. I mean, it's not something that the reservoir is going to, dam is not going to burst if you don't have this survey done. So you can postpone it year after year, and as a result, many reservoirs in the United States have never been surveyed. So the full contour survey, a cloud of data points, most complete information available, but it's also costly, especially for large reservoirs. If you have a small reservoir, 1 or 2 days in the boat running the survey, that's not a big deal. But big reservoirs, tens of kilometers long, you're looking at a lot of boat time. So this is where cross-section surveys come into play. Traditionally, cross-section surveys were used for all reservoirs because we didn't have GPS equipment, computers that we use to develop the full contour surveys today. But cross-section surveys give very good results. They can be very accurate. And there are methods to correlate cross-section surveys to a complete contour survey. So by surveying several cross-sections, you can track the evolution of deposits over time, the loss of volume over time, without doing a complete survey. A longitudinal survey is basically longitudinal profile. And if you don't have much money, you can't do a complete survey, running a longitudinal profile will give you a good indication of what's happening. It'll tell you how the reservoir delta is advancing. It'll show the increase in the top of the reservoir level on the top of the delta and also in the fine sediments. It gives you a good snapshot. And one of the Bureau of Reclamation publications on reconnaissance surveys, which you can get off of their website, does give an example of how to use longitudinal surveys using a multi-beam sonar to give pretty good information using a partial survey. It's a very cheap method of looking at how the reservoir is evolving without having to do a complete surveys. Now, all the methodologies are going to incorporate an error. 1 or 2% you should anticipate. In fact, you can take the same data, the same digital elevation map data, put it in different software, and you'll get different answers. So be aware that it's really important that you can have consistency in your methodology. And in my opinion, consistency in methodology over time is more important than absolute accuracy. You're not so worried about, am I accurate to within 1%? What you are concerned about is, if you're looking at a 5% change in volume, how much of that is due to an error due to change methodology, and how much of that is due to actual sedimentation? Because in lots of surveys, we see really erratic results. Also, there's some not controversy, but the question of, should we use single beam or multi-beam? Single beam surveys are good. You get really good data with them. And it's a pretty straightforward technique. Multi-beam surveys can accelerate surveys in large and deep reservoirs. You get a lot more data points a lot quicker, but they do require more sophistication in the post-processing. And if you're in a situation where you can have errors, multi-beam survey will definitely find those errors and give them to you. LiDAR can be used when the reservoir is at a low level. Photo or satellite images can be used holding the reservoir at different levels. So if you have a satellite image at different dates when the reservoir is at different levels, it's like making almost like a contour map. You have the water surface area at different levels on different dates, and you can determine volume from this. And you may have land surveys. So here's a little reservoir. We've got 151 cross sections, an awful lot of data. You can make a very complete contour map with this. But let's say you wanted to do a reconnaissance survey. Let's say it's been 5 or 10 years since the last survey and you're not sure what's happening. What can you do? You don't really have in the budget. Maybe you've got 5 reservoirs in your area. You don't have money to do all 5 of them, but they gave you some money to do some survey. You could go to all these reservoirs and you could do a longitudinal profile, say start at the dam and just run up the center line, run up the main branch and run up the side branch. And this will give you a pretty good idea of whether something really exciting is happening, if you're going to be worried, or whether it's pretty much doing what we thought it was going to be doing. Or you could survey every 5th line or every 10th line. And again, it's not a complete data set, but it gives you a pretty good idea. And if not a lot is happening, reservoir deposits tend to be flat on the bottom. So you can get an update of what's going on. Got to be careful calibration your equipment because, and this shows a survey from a reservoir we looked at a couple of years ago. The client asked us to look at these data. Notice that it looks like a little herringbone pattern here. This reservoir is unusual because in this particular area, a survey was done in an east-west direction, then on the following week in a north-south direction. And what happens here is you're looking at improper calibration of the equipment. So these herringbone and different lines occur because there was about a 4-meter miscalibration between the first survey and the second data survey. So even though these points are all at the same elevation, the data show that they are at different elevations. And so you get this really strange looking bottom pattern. Now, we found this error because the cross sections were crisscrossed. You almost never do that. You go back and look at our prior example here. You would never catch that problem in this type of a situation because you don't go back and re-reference. That's why, for instance, it's a good practice to run a longitudinal profile along with your regular survey data so you can catch calibration errors. Also, it's good to calibrate your survey instrument, your sonar, every day, depending on where you are. If you're going to be working in this area of the reservoir, the water's shallower and warmer, you don't want to calibrate your instrument in this area of the reservoir where maybe the water's colder. You want to calibrate your bar check, your depth check, and your sonar where you're going to be working that day. So data inconsistencies lead us to problems like this. This is a reservoir that has been very consistent, has very good data sets, and all of a sudden they changed survey companies and they get this kind of result. We know the reservoir didn't get bigger. There are just errors and problems. And this is why it's really important to have consistent results. Here's some information from from a group of reservoirs in the United States on the East Coast. Notice that we have bathymetric errors. We have a number of reservoirs here that are growing larger over time. Why does this happen? Because there's an error. In this case, probably the original survey was done by one method before it was a pre-impoundment survey, and then the bathymetric surveys are done by a different method. There's errors on both of these survey methods, and the errors probably are in opposite directions. So they're in the same direction, which gives us the appearance that we have an increase in reservoir volume. But these errors are not limited only to these reservoirs marked in red. These errors also occur on the ones that are in black. We just don't see them because they are in the opposite direction. So the one takeaway from this is you want to minimize the problem using a consistent methodology. You need to start your first reservoir survey as early as possible and on a new reservoir immediately following initial impoundment. And errors, look at the range of errors. We're looking at 7% errors. So, these errors do exist. They are real. Change in methodology is the #1 source of error. You change from a contour, you go from a cross-section survey to a contour survey. You're using a more modern technique, but you need to take that contour survey and replot the volume due to by both old and new methodologies to find out how much of that change is due to error and how much is actual sediment. And repeated bathymetric surveys are the only way you're going to see changes in your rate of sedimentation over time. If we don't have that, we might take the initial value, some value later in time, and then project, well, this is our rate of sedimentation. But if we had more complete data, we might say that, no, it's actually looks like this. Look at the red line. This is the declining rate of storage loss in the conservation pool detected by successive surveys. Big differences. So you need successive surveys to see what's going on over time. And finally, successive surveys can be plotted in a longitudinal way to give you a very clear picture to yourself and also to decision makers of what's happening underwater. Nothing is as nice as the picture, and this is a very clear way of demonstrating what's going on and you yourself also understanding it as an analyst. Now, suspended sediment transport. We need this for sediment transport models. We need it for evaluating sediment routing techniques, off-stream reservoir sluicing, etc. But the challenge is that sediment is highly variable in time and space. The amount of sediment that's transported by a river in 1 hour of peak discharge may be 1,000,000 times more than is transported by the same river at low flow. You have much more discharge, maybe 1,000-fold increase in discharge, and 1,000-fold increase in sediment concentration. So the peak events, it's highly variable, and the peak events are really important. So unfortunately, these peak events, floods, hurricanes, etc., are inherently difficult to sample. You also have a problem of constructing an accurate sediment rating curve once you have the data. And this is the biggest area where we have the potential to improve the quality of data, because I see lots and lots of errors in this. And finally, we have to estimate the unsampled load. Part of it's a bed load. Part of it is a contribution from extreme events. So we look at a sampler. We have a sampled zone and an unsampled zone. And this unsampled zone includes the material that rolls along the bed. This is part of the problem in estimating the bed load, the unsampled material. But when we developed our rating curves, we're using only this suspended sediment sample. And the first thing we do is we take these data, which are expensive to collect, and we put it into a spreadsheet and we throw an Excel trend line. Now, this trend line does not predict sediment yield very well. It's not a good predictor because it's looking at a least square between the data. And in this example, for instance, we have a lot of data at low flow, and you'll notice that this group of data pulls this curve down on the left-hand side of the graph. And as a result, it goes high on the right-hand side of the graph. This is all the data. This is the data that counts. This is where the sediment's being transported. Basically, nothing is happening over here. You have low flows and low concentrations. You would be much better off by just throwing away all of this data. You would get a better fit to the actual data that counts. Here's an example showing the Excel line and the adjusted equation. The original data set, if we take each point and compare it, if we compute the sediment load for each data point and then compare that to the sediment load which is predicted by the equation, we'll find out that the original data set has obviously 100% of the transport, but the Excel equation is only predicting 37% of the transport that's in the original data set. So if we take the Excel equation and apply it to a long-term discharge data set, we are going to have only 37% of the actual load. If we adjust this equation, we can adjust it by using the Excel solver, for instance, using as an objective function reproduction of the actual loads in the data set. We're looking at 99.9% of the load. Now, we also typically want to construct these graphs based on concentration versus discharge and not load versus discharge. Here we have a graph of load on the left versus discharge on the x-axis. And you see that load and discharge, there is some correlation here. In fact, there's an R squared of 0.5. And you say, well, R squared 0.5, sediment data, that's not really that bad. But this whole thing is a spurious correlation. Here's your original data set. There is no correlation in the original data set when we look at concentration versus discharge. So this gives you this just by changing it to load instead of concentration. R squares in sediment transport have, in creating a sediment transport rating curve, have nothing to do with what is going on. They just forget about R squares, and all you want to worry about is, can I take this original concentration data set and apply the discharge concentration, multiply them together, and generate my original discharge volume, discharge quantity of sediment. Now, when you develop discharge rating curves and sediment rating curves, the mathematics will take the data and will just work blindly with them. But if you look at this data set, you'll see that you should have a kinked curve, a curve that has two segments to it. Use your mind, use your eyeballs, look at the data, and make sure that you get something that makes reasonable sense from the real world, not a mathematical best fit. So there is a methodology to do this. There's a publication which is called Extending Life of Reservoirs, Chapter 6. It's referenced on the last slide. You can go there in Chapter 6 and get the methodology. Now let's look at the episodic loads problem. Here we have some data. This is from a gauge in Puerto Rico. This is from a gauge in California, Santa Ana River. And you'll see that you can have these extreme events that basically dominate the loads. They may not be in your data set. Here's one from Hurricane Georges. And you see this, and what's happening when this happens? You're getting events like this. This is Caunias Reservoir, which is just downstream of that gauge. And you have a sedimentation rate, and all of a sudden, we get a hurricane, and we lose equivalent of 50 years of normal volume lost due to normal sedimentation. These events are big, they're important, and when you adjust for your load, your long-term load, you need to think about episodic events and the possible role they may play in the long term. Also, you may not think about it, but there are other sources of data. For instance, this is from a power plant, and you've got the reservoir level, and these are data points for the sediment discharge taken at the turbines, because turbines are affected by sedimentation and abrasion. So you can use these data to also complement whatever data that you get from a regular sampling program. Grain size of sediment deposits. Why important? Again, it's data that you need to calibrate and run your sediment transport model. You need it to monitor the approach of sandy sediments to infrastructure such as an intake, which could be leading to a turbine which could get damaged by abrasion. Dredging cost analysis and disposal options really depends on the grain size. Challenge is to get a representative sample and the trade-off between sampling cost and data quality. Again, remember the photo we showed earlier that we have the multiple layers layering within, particularly in deltas. You can't just use a surface grab sample. You want a core. Here's a core from vibrant core from Dos Bocas Reservoir showing sand and silt and clay. So by having a core, you can see that the silt and clay, these two types of material exist in this portion of the reservoir. This is a vibrocore setup. This is portable vibrocore. You've got the floats to keep it vertical. You've got the vibrating head. You've got the core tube. You've got some weights. So you've got a winch and a portable tripod. You pull up the sediment in tubes, and it can be extruded, or the tube could be cut open. This is what the thing looks like set up on deck, along with a GPS, so you can determine exactly where your sediment sampling was taken. And it's all battery powered. So you go out in the reservoir, you set up your system, you operate it. Your depth depends on how much cord you got. This thing will operate about to 60 meters deep. And this is another view of this same setup. This is portable equipment. This particular system, we carry it on commercial aircraft as luggage. It takes three people's luggage. But yeah, it's portable. If you got a pickup truck and you're working in the States somewhere, highly portable. Now, when you're sampling the fine material, it seems to be pretty uniform. But on the deltas, you got a real problem. Look at the structure of the delta deposits here. You've got a river that flows across a delta, and then you have these sands on the levees when the river starts to overflow, or when you have turbidity current carrying sand that overflows under submerged conditions. And as you move away from this channel, it becomes finer material. This particular photographs on Nurek Reservoir in Tajikistan, and this was a sampling point that was used. If you walk away from this channel about 100 feet, you start getting into quicksand. I mean, and you simply cannot go there. So your sampling is dictated by where you can get to. A really good example of this, if you go on Google and look at some of the reservoirs in Kansas, for instance, like the Tuttle Creek Reservoir, you'll see how you have the river flowing across a delta, and you can see how that you have vegetation on these deltas, on these levees on either side, and the material on the other further away is going to be finer material. So if you're sampling a delta, be aware of this. And if you are sampling from a boat with submerged conditions, you would want to take samples at multiple locations across the delta. You can also possibly use a sub-bottom profiler. You can see you get a first reflection off the top of the sediment, and a second, and you can get a second reflection off of the original bottom. But you will not get this if there's gas in the sediment, because gas creates an air-water interface, and it strongly reflects all these signals. Now, turbidity current, monitoring turbidity currents. Turbidity currents are important for the transport of fine materials in reservoirs. And this material, as we mentioned previously, can be vented from some reservoirs to reduce significant sedimentation. And again, you have the challenge of the trade-off between sampling cost and quality of data. And you can observe from bathymetric data that turbidity transport does occur, but it's a bit of a challenge to try and determine from that how much you might be able to release. Remember, the turbidity current comes in, flows along the bottom, and can create this muddy lake deposit, which will create consolidated deposits. Here's the turbidity current entering the reservoir and plunging. This is the plunge line. You see the very distinct change in the color of the water, because the turbid water here plunges and flows underwater. And you'll notice also that as this flow plunges, it creates a surface countercurrent. And so you have floating debris that comes downstream. It gets caught against this countercurrent, and it will accumulate along the plunge line. And here we have plunge line in Haiti, where we have a reservoir that has a lot of floating debris, and it gets trapped at the plunge line. These guys are collecting the larger logs to make charcoal. So you can vent the turbidity currents, particularly when they create these lakes, submerged muddy lakes. And this is what you want to understand whether you can do or not. Here's an example from Taiwan of the construction of what they call an elephant trunk intake to siphon these turbidity currents as shown here, where you siphon the turbidity current, and here you siphon the turbidity current. So you can look at the bathymetry data, and you can see this in the data. Here's an example. You'll notice the horizontal deposits here in this reservoir. The intake is at a high level. The turbidity current comes, creates a muddy lake, and deposits and creates these horizontal deposits. Very, very clear evidence that this particular reservoir transports a lot of sediment to the dam by turbidity current, and this could be discharged. Now, some reservoirs, you'll see that it goes continuously towards the dam. Turbidity currents may be important, but they don't transport a lot of material to the dam. It gets dumped along the way. You can monitor turbidity currents in real time. You can put an array of instruments in the water column. You can have it permanently anchored in the reservoir, or you can deploy a boat with a water quality sonde or sampling devices during inflow events. But if your inflow event's a hurricane or something like that, not very feasible. You could also monitor upstream, say above the plunge point, and also at the dam using a low-level outlet. For instance, water being taken into the turbines or a pump sampler. You could use a current velocity profiler. Here's an example of a floating platform which has an instrument array at Xiamen Reservoir in Taiwan. They have 3 of these up and down the reservoir so they can monitor the movement of the turbidity current. And finally, we're going to talk a couple of minutes about adaptive strategies. If we go back, in not every instance will it be possible to halt sedimentation, to reverse sedimentation. So we will, in many cases, end up with a gradual loss of capacity. What do? One thing that's done pretty frequently in the United States is pool reallocation. For instance, the Corps of Engineers has a lot of reservoirs that have a flood control component and a conservation component, and maybe a couple of other components, maybe an environmental component. And the rate of sedimentation of these different pools is not uniform. Typically, the conservation pool is more impacted than the flood pool. Why? Well, the flood pool is normally empty. And the conservation pool, not only does it normally have water in it, but it's at a lower level than the flood control pool. So the sediment will tend to accumulate in the lower part of the reservoir. Not always. Your delta will tend to come in from above, but if the flood control pool is normally empty, you typically will get less sediment. And from looking at data from a number of core reservoirs, it looked like the flood control pools were accumulating sediment about 1/5 of the rate of conservation pools on average. Of course, there's some that do faster, some are much slower, but more or less 1/4 or 1/5 as fast. Water conservation. If you are looking at reduction in water supply availability because of storage loss, you would possibly look at water conservation and more efficient use. Agriculture, of course, is a big water user. You may switch to more water conserving irrigation techniques, or during periods of high water availability, you may take water and put them into the aquifer. For instance, conjunctive use, using the reservoir with groundwater to maximize the total water yield from all sources. Structural modifications. You may modify your intakes as sedimentation approaches. You may put protective coatings on hydropower turbines. And you may end up developing new and sustainable sources of water or power. One of the interesting things about hydropower is that it typically, the loss of storage capacity is not going to have a substantial impact on your ability to produce power. It may go down 5 or 10% as a result of lost storage for the reservoirs and hydropower systems that we have looked at so far in several countries. But what happens is that if you have a storage reservoir that is storing and delivering power during the dry season, that power loss of your ability to deliver dry season power is basically going to disappear in a linear fashion at the same rate that your volume available for water storage disappears. So, for instance, if I have a monsoon climate, have a very dry winter and a wet summer, say 3 months of wet summer, June, July, August, if I lose my capacity, I will be able to deliver a lot more power during the wet season because I'll just be running the turbines continuously instead of refilling my reservoir to supply power during the dry season. So total amount of power doesn't get hit so badly. Dry season power gets hit very badly. And of course, you also have the need to maintain what they call daily regulation storage, pondage, which gives you the ability to turn a turbine on and off during the day by storing the water that comes in during the dry season. And this is important from the standpoint of operating a hydropower plant together with intermittent renewables such as wind and solar. So here's an example of conjunctive use for a project we got here in Puerto Rico. We've got a reservoir, it's lost volume because of sedimentation. It also has been forced to do a drawdown. And this is a project that the Bureau of Reclamation has worked with the Electrical Energy Authority on helping them to define management options from the standpoint of dam safety, because this is a hydraulic fill dam built in 1914, and the earthquake danger, the earthquake hazard in this area has been determined to be significantly higher than was originally thought to be. And as a result of the increased hazard from earthquake shaking, it became necessary to lower the pool. So in this reservoir, it currently discharges about 60%, more than 60% of the inflow is discharged to the sea. And we set up a procedure to take water from the reservoir when it's within about 2 feet of spillage and delivering additional water to a recharge area so we can supply water to a community that's supplied only by wells. So basically the reservoir looks like this. We've got a recharge pool, a conservation pool, and a rationing pool. And anytime the water levels in the recharge pool, we deliver an extra 15 cubic feet per second into an existing irrigation canal, which delivers it to recharge areas. So we're using the reservoir storage plus the aquifer storage together so that we're operating the entire water supply system, ground plus surface water, as a system, as opposed to surface water supply completely independent of groundwater. Of course, here and elsewhere, you have the problem to overcome, a bureaucratic problem, let's call it, or administrative problem, or political problem, is that traditionally, these two sources of water supply have been managed separately and probably managed by different agencies. And you need to overcome these types of challenges to be able to implement adaptive procedures. But if you can't do that and you don't have the money or the wherewithal to remove material from the reservoir, this is a good option. One closing remark I'd like to say, because I think this is the last slide, is we looked at the option of conjunctive use in North Coast reservoirs in Puerto Rico with groundwater on the North Coast. And we found that by restoring reservoir capacity, by offsetting 20 years of sedimentation, we could increase the reservoir firm yield on the order of 4 to 5 million gallons a day. But by going to conjunctive use and not dredging, we were able to give a 20 to 25 MGD increase in firm yield. This is an extraordinarily large increase in firm yield, and it is can be achieved at about 1/5 of the dredging cost. And whereas dredging will be offset by continued sediment accumulation in the future, the conjunctive use is not. So I leave you with these ideas. There's a lot of management techniques that are available. The best technique will probably be a combination of techniques. Some techniques may be used first, others may be used later as sedimentation becomes more advanced. Plan today for the techniques that you will have to implement, not only today, but say 50 years in the future. And you need to monitor to know how to optimize what you're doing. 2 resources, both of them for free on the internet. You can get both of them at reservoirsedimentation.com right here, reservoirsedimentation.com. This is also, the extending life of reservoirs, also available from the World Bank. Just Google extending the life of reservoirs and it'll take you straight to the World Bank site and you can download it from there. So that ends my presentation, and I'm willing to answer any questions you may have.
Great. Thanks, Greg. That was a great talk. Very much appreciated for volunteering to do this. Let's see. So people that are on the line, if you have questions, just send them over to myself or Tim. You might actually just have a panelist option, it sounds like. Go ahead and type those in and we will collect those and ask Greg. Okay, we have one here. Can dam owners afford not to monitor sedimentation?
Yes and no. The correct answer is no. The practical answer is yes, because a lot of them don't do it. So, you know, if you were looking to to sustain your system in the long term, you really do need to monitor. But a lot of people don't, including U.S. federal agencies, and there's a lot of dams that are not regularly monitored. Interestingly, in Colombia, Colombia has about 60+% of its total energy, electrical energy, supplied by reservoirs, hydropower. And in Colombia, the reservoir owners are required by law to do, well, I don't know if it's law or regulation, but they're required to perform a reservoir bathymetric survey at 5-year intervals. So, because it's very important to Colombia for sustaining their power supply.
Yeah, it's interesting that we don't have that here in the US yet.
Most countries don't have a requirement of that type. That's why it makes it interesting that Colombia does. But you know, Colombia is very dependent on hydropower.
Okay, here's another question for you. How would you engage with managers to help encourage monitoring for more efficient operations?
That's an interesting question, because I mean, it's one that I find repeated all over the world, and there's no easy answer to that one, but it's probably quite site dependent also. But I would look at the types of services that the reservoir provides, and based on that, I would try and emphasize the importance of sedimentation or sediment management. You know, at least knowing where you are, to being able to continue to deliver these services, and most particularly, you might say that we wouldn't want to have a surprise when, for instance, we have a drought and the reservoir level goes down and all of a sudden we're not quite sure what the volume is, and there could be a lot of bad press and a lot of a lot of questions about why haven't you been doing this. Surveys are cheap. They don't cost that much money. They don't have to cost that much money. They can be very expensive, but they don't have to cost that much money. So I would encourage you to use that type of an approach. And just to give you a general idea, on a small reservoir where you're not looking at more than 1 or 2 days of boat time, you're looking at, and the boats are going to be running at about 3 or 4 miles an hour. You're looking at maybe $30,000 for a survey. So, you're not talking about really, really big numbers. And if you have a pretty big reservoir, there's ways that you can do an abbreviated survey. And again, I refer you back to the Bureau of Reclamation's publication on reconnaissance reservoir surveys as something that may be interesting and useful to you. Mm-hmm. That's about on Ferrari.
In some ways, it seems a little bit like a chicken and egg question, at least in my experience, that a lot of the reservoir owners don't really know how much sediment is coming in, and so they don't realize it's a problem, so they don't think that there's a survey needed. So,
and that's why I think that the saying that you wouldn't want to have a surprise is probably, I would expect, the most logical way to approach this, because no one likes surprises.
Yeah. Okay, so one last question here. How do you calibrate the sediment rating curve to match the reservoir survey estimate of sedimentation?
First of all, you have to recall that both of these have errors in them. This reservoir volume, you can get that within a couple of %. But what you don't know is the bulk density of what's in the reservoir. So first of all, you need to know the grain size, because if you look at the conversion of bulk density to versus grain size, it varies quite a bit. If you have relatively fine sediment, you may be looking at 1 or less than 1 ton per cubic meter, dry weight basis. But in sandy delta materials, you may be looking at as much as 1.6. That delta in Tarbella that I showed you the photo of, which was 50% sand, fine sand, and 50% silt, no clay to speak of, that was 1.35. So you have a pretty large range in your bulk density. And the average bulk density may not be exactly an easy number to come by, because you'll have part of the reservoir with a delta with a high bulk density. Part of it near the dam may have fine sediment with a much lower bulk density. That's a big potential source of error. And you need to be thoughtful on how you approach that. Another thing to remember on your suspended sediment, be sure that you look at the methodology that's outlined in this book on extending life of reservoirs, chapter 6. Because sediment rating curves, if you've done it with a trend line in Excel, I can almost guarantee you it's wrong. And they tend to underestimate. Generally, they will underestimate your sediment yield. So you've got data, make sure that you process the data accurately. And finally, the last thing is this problem of the episodic nature of transport. If you've had a couple of big events that aren't in your sediment database for your suspended sediment, you may have events that you can't really represent or understand with the database that you have. You will take your data typically and you would extrapolate your rating curve to higher discharges, but it may or may not be accurate to do that. For instance, depending on where you are, you may have a landslide threshold. So once you get a certain level of rainfall, this is particularly true in humid tropical mountainous areas, humid mountainous areas. You can get, actually I think it's probably typical of any mountainous area, but you can get these a change in your erosion process from a surface erosion to a mass wasting process. I mean, you've seen like the area around San Francisco in California, you see beautiful examples of these soil slips. So imagine a very big storm and these things occur everywhere, and you've changed from surface erosion to mass wasting. And this may give you a lot more sediment than would be predicted by your curve. So those are the types of errors and problems that I would look at in terms of trying to rectify the both sets of data. And you may end up adjusting both of them to get to some reasonable number that seems to make sense.
Great, excellent. Thanks, Greg. I really appreciate it. We're going to call it there. So thanks very much for giving the presentation. Great presentation.
Very good. And thank you for the opportunity to speak to everybody. Have a good day.
All right, sounds good. All right, we'll go ahead and end the meeting now. All right, thanks everyone.